Welcome to AP Chemistry at Honolulu High School. I'm Brian Brown, and today we'll be starting Chapter 11. Along with Chapter 10, this comprises a decent chunk of questions on the AP test. Chapter 11 alone, you're typically looking at about 4 of the 75 multiple choice questions, and FRQ occasionally. So it's not every year, but some of the ideas in this chapter are represented in most years on that portion of the AP test. Now first, 11.1 gets into comparisons between gases, liquids, and solids. And what you need to understand is while they have a variety of different properties, the fundamental difference between these states is really a matter of distance between the particles. In a solid state, your particles are packed close together. Liquid, relatively close, but space in between, so now they're free to move around. And in gases, they're farther apart than the other two. So in the gaseous state, the particles are um, moving independently, basically filling the size of the container. So they take the volume of the container, and the particles are significantly farther apart than in the liquid and in the crystalline state. So a fundamental difference really between the three would be the distance between the particles. And that's really created by some of the things we looked at last chapter with kinetic molecular theory. And in the different states, then, we have a variety of different properties, things that would be true about solids, liquids, and gases. Now, because of the solid and liquid state, the particles are much closer together. These are often referred to as the condensed states of matter. So liquids and solids would make up condensed states of matter. And these are the states of matter that have intermolecular forces. That's why they are close together, because the particles exert attractive forces on each other, holding the particles relatively close together. And when you break those intermolecular forces as the particle speeds increase, then eventually you become a gas. Now, the state of substance is in. So are you a solid, liquid, or gas? It really comes down to two antagonistic forces. So at a given temperature and pressure, are you going to be a solid or liquid or gas? It really comes down to the what's happening with kinetic energy. And kinetic energy is a force that breaks attractions versus those attractions themselves, which would be the strength of the attractions between the particles. So typically what we're looking at here is our intermolecular forces. So you have two competing things, the kinetic energy of the particles versus the strength of attractions between the particles. Which of these forces dominate determines whether you're going to end up being a solid, a liquid, or a gas. Now, section 11.2 actually gets into the different types of intermolecular forces. So here's really where we're looking at the force of attraction between substances. Now, the term intermolecular here, inter means between, molecular means the greater idea of molecular. So we're not just looking at molecules, we're looking at molecules, atoms, ions, a variety of different things. So we're looking at forces of attraction between different types of particles. Now, one thing that is very, very important is you understand the difference between inter and intramolecular forces, both of which will be forces that we'll be studying and looking at in chapter 11. Now, inter is the force of attraction between molecules, and that's a significantly weaker force than the intramolecular forces, which would be the forces that hold compounds together. So an intramolecular force would be the bond between the hydrogen and the chloride here. Covalent bonding is a type of intramolecular force, a within force. And as a general rule, intramolecular forces are in the order of or magnitude of 10 times stronger than your typical intermolecular force, which means intermolecular forces are going to break significantly easier than intramolecular forces are, which is why you can go from a solid, a liquid, to a gas. You're playing around with differences of intermolecular forces there. Those are forces that are significantly weaker than intramolecular forces. So you're much more likely to send a solid to a liquid than you are to break the solid's bonds apart and force a chemical reaction. So as a general rule, it's on the magnitude of about 10 times between intermolecular forces and intramolecular forces. And knowing and understanding the difference between the two is incredibly important. So this is a fundamental idea on the AP test and for this chapter. Know what intermolecular forces are and know what intramolecular forces are. How are they similar and how are they different? Now, intermolecular forces, however, are strong enough to control our physical properties. So things like boiling point, melting point, vapor pressure, viscosities. There's a whole host of properties of solids, liquids, and gases that are really driven by differences in intermolecular forces. And these intermolecular forces between neutral molecules are referred to as van der Waals forces. So we're looking at attractions between neutral substances. They're collectively known as van der Waals forces. There are other types of in-between attractions, but neutral force attraction would be collectively known as a van der Waal force. Now, some fundamental types of van der Waal forces, and these should look familiar to you. We may not have called them that in pre-AP chemistry, but London forces, dipole-dipole, and hydrogen bonding are all types of intermolecular forces that we studied in pre-AP chemistry, and we also looked at not all that long ago back in chapter 8 and 9. So these are our fundamental intermolecular forces that would be between neutral particles. Now, if you don't have a neutral particle, let's say you have an ion, there are other in-between types of forces we can have. So these are intermolecular forces, but they're not van der Waal forces because now we're not looking at all neutral particles attracting each other. So if you have an ion that is attracted to a polar molecule, polar molecules have polarity, so they have a dipole. So we have an ion-dipole attraction. So another type of intermolecular force would be ion-dipole. And then the final type that's listed here, and this is really an intramolecular force, but in some respects we're looking at forces between things, in this case between ions. But this is where we'd get classified as really what we'd call an intramolecular force, ionic bonding, attraction between ions and other ions. And these are a strong type of attraction. So as a general statement, these 1 through 5 here are a general way of looking at strengths of intermolecular forces as well. Uh, but you have to understand it's a general statement because London dispersion forces, if the particles are large enough, can actually rival the strength of dipole-dipole and hydrogen bonding or surpass them. So sometimes London dispersion forces can be a very strong force. But in general, this is a list in order of weaker to stronger types of forces. And the neutral ones, the first three, those are also known as van der Waal forces. Now the first one we're going to look at is the ion-dipole interaction. So it's a fourth type of force, and this really is important to solution chemistry. When we've got water, which is a molecular substance, so if we were to draw water as a very simple structure, it has two poles, a positive and negative region. So this would be an oversimplified way to draw water. So this is more likely something like hydrogen chloride, um, hydrogen fluoride, where we have basically a polar molecule type situation. Well, it's got a positive and negative end as a polar substance. That's our dipole part. We have two poles, that's a dipole. Any polar molecule exhibits a dipole. Well, part of that dipole, the positive or the negative end, can be attracted to ions of opposite charge. And we've got a partial positive and negative attracted to a two positive and negative. So this is a stronger attraction typically than a dipole-dipole type interaction. So in the case of something dissolved in water, we've got water which has a dipole, and our ionic compound, if it's an ionic compound, would give us ions. Water would hydrate, surround, and hold on to those ions. And that ion to dipole attraction is actually a fairly strong attraction, and they're in many situations much more strong, or I should say, stronger than the dipole to dipole interaction. Otherwise, the water molecules would all stick to each other and not hydrate and pick up the ions. So this would be a fourth type of attraction. And the strength of these forces are what really make it possible for ionic substances to dissolve. Since this is a very strong force, it's likely when you put these ions in water that the water molecules will stick to the ions rather than each other. Now the next type would be the dipole-dipole interaction. And this is what we typically get with polar molecules. So molecules that have permanent dipoles, which is what a polar molecule is, contains a permanent dipole. So they always contain two dipoles. And these dipoles can interact with each other. So as these particles are moving past each other in the liquid state, they would exhibit attractive forces. What they're going to do is line up to maximize attractions and minimize repulsions, but realize as the molecules move, kinetic energy plays a role here. So they don't lock in a rigid shape if the kinetic energy is high enough. Kinetic energy allows these molecules to push past each other, but they do tend to align and move by those attractions and repulsions. So the positive end of one is attracted to the negative end of another, and vice versa. And these forces are only important when the molecules are close to each other. So if the particles are moving fast enough to overcome these attractions, high enough kinetic energy, they'll become a gas. And these attractions become irrelevant when they're far apart and moving quickly. But when they're moving more slowly and they're close together, these become very significant forces in terms of behavior of um, molecular substances together, like a glass of water. Now, dipole-dipole interactions. A general rule of thumb when comparing different types of dipole-dipole interactions, the more polar the molecule, the stronger the intermolecular force, and therefore the higher things like boiling point, melting point, the dipole moment, which is a ranking of the strength of attraction of the dipole, the higher those things are going to be. So the more polar the molecule, so if you're looking at molecule polarity, significant differences in electronegativity causing very large partial negative and partial positive regions. So very polar molecules, they're going to have stronger dipole-dipole interactions, which means they're going to be harder to boil and to melt. Now, London dispersion forces. This is something that you looked at last year, but I want you to have a much deeper understanding of what's happening here. It's not complex, but you really have to understand the general situation. So let's look at a typical helium atom here, because the helium atom has 2 protons and 2 electrons. So it's a relatively simple atom. Now, the electrons are in the 1s orbital of the helium. And remember, electrons, as like charge objects, are going to tend to repel each other. And therefore, they tend to stay far apart, which means they tend to stay evenly distributed around the atom. But at any given point in time, because the electrons are in constant motion, they might both end up on the same side. So while typically this is a nonpolar situation, an even distribution of electrons in the electron clouds, at any given point in time, you might end up with the electrons on the same side. Now, when that happens, what you're going to get is a momentary dipole. So at that instant, the helium atom is actually polar. It's got an excess of electrons on the left side, and that's going to make the left side slightly negative and make the right side slightly positive. So at that point in time, the helium atom really does become a temporary polar substance. And that's really what London dispersion forces are. They're unequal distributions of electrons in the electron cloud created by movements of electrons. Now, one of the things you really didn't get into last year, because what I just talked about is something you should have really looked at in pre-AP chemistry. But what you need to understand is the importance of that momentary dipole to the electrons in the electron clouds in the other atoms around the substance. So if we have another helium atom nearby, so once again, we're looking at situations that we're more likely looking at liquids and solid interactions here because the particles are close together. So this is going to happen more often in a gas, unless the gas particles become close enough together. So in and around collisions, this can happen. So if we have a helium atom nearby and one atom creates a dipole, remember that's going to make that side of the atom very, very negative. Well, that's going to end up causing in the electrons of the atom nearby a movement of electrons there. So what really happens is we induce a dipole in another substance. And this is an important component of London dispersion forces, is you can create this momentary, temporary dipole in one particle, and that induces dipoles in nearby molecules and causes them to attract each other. Now, these forces are present in all molecules. So you need to understand, even in a polar situation where it's a dipole-dipole attraction, the electrons are in constant motion. You're going to create these momentary stronger dipoles. So London forces are typically a weaker type of force, but they can be very significant. And all molecules, every last one, even when we talk about dipole-dipole situations, so polar molecules or dipole-dipole, they also have London forces. It's just the London forces themselves may be significantly smaller than the dipole forces in many, many, many situations. So all polar and nonpolar molecules have London forces. That's an important distinction to remember for the test and the AP test. Everything's got London forces. They're just most relevant often in nonpolar substances. The tendency or ability of an electron cloud to distort in this way is what's known as polarizability. The larger the electron cloud, the more polarizable it is. So the greater the surface area of a substance, the larger your electron cloud is going to be, the more likely you're going to induce these dipoles. So a way to remember this is larger, more polarizable electron cloud. I'll often refer to that as LIMPEC. Now keep in mind, on an FRQ question for homework or on an AP test in an FRQ, you can't write LIMPEC. You need to actually say it's got a larger, more polarizable electron cloud, and therefore it creates whatever. So LIMPEC is an important acronym for ideas in this chapter, especially when we're looking at London forces and the strength of those London forces. And this has a huge impact on melting point, boiling point, viscosity, vapor pressure, all kinds of different things. So it's a really important distinction, this LIMPEC idea. Now, the shape of a molecule can also affect the strength of dispersion forces. Long, skinny molecules like pentane, straight chain pentane, have stronger dispersion forces than short, fat ones. And that's because even though they have the same number of carbons, when you have more branches, it lowers your surface area. And lower surface area is a less polarizable situation. So long, skinny molecules are going to have higher melting points and boiling points, stronger intermolecular forces, stronger London forces, because of the fact that they have LIMPEC, larger, more polarizable electron clouds. So these short little circular molecule like 2,2-dimethylpropane has a boiling point of 282.7, whereas the exact same molecular formula, but in a different arrangement, a straight chain form, is 309.4. So you can see that it has a higher boiling point. That must mean it has stronger intermolecular forces. Well, the reason would be the greater surface area of the long, narrow thing compared to the fat one. So this is due once again to the increased surface area, making it more polarizable. Larger surface area, LIMPEC, larger, more polarizable electron clouds in a larger surface area situation. Now, the strength of dispersion forces also tends to increase with molecular weight. Now, you got to be careful. You cannot use this as a discussion on the AP test. So you can't say it has a higher boiling point because it has a higher molecular weight. What you need to understand is a higher molecular weight is LIMPEC, a larger, more polarizable electron cloud. And that's what you have to use for this. So be very, very careful. You will not get it right, and you won't get any points on my review if in the FRQ you tell me, well, the reason it has a higher boiling point is because it's got a higher molar mass. You can't do that. What you have to say is a higher molar mass is more electrons, which makes a larger, more polarizable electron cloud. Know it, use it. Just don't write it as the acronym. Now, I mentioned that all substances, polar substance included, have um, dispersion forces. So they have London forces as well. So when you've got a polar substance, which force is more important, the dipole-dipole interaction or the dispersion force interaction? Well, really what it comes down to is size and shape. So if two molecules are a comparable size and shape, the dipole-dipole interactions are more likely to dominate. But if one molecule is significantly larger or longer and less branches, it's going to have a greater surface area, then it's probably going to be the London forces. And that's once again because LIMPEC becomes important. When you get a large enough electron cloud, those momentary dipoles happen significantly more often with significantly greater strength, inducing those in nearby molecules as well. So if they're comparable size, then the dipole-dipole is more important. If they're not comparable in size and one is much larger, then it's really going to be about the dispersion forces and that whole LIMPEC idea that can become large enough to dominate. So which is more important? It really depends upon the general size. Now, using these ideas to explain things like melting points, you need to be able to do that. So let's say we have a graph here. You can see it's molecular weight versus temperature. And this is a non-polar series. So if we, or I should say, the bottom one is a non-polar series. The nonpolar series on the bottom is going to follow a very specific trend in boiling point temperature, and it's because of larger, more polarizable electron clouds. So in the bottom situation, we're not looking at polar molecules, we're looking at nonpolar molecules. So how come something like SNH4 would have a significantly higher boiling point than the others? Well, it's about molecular weight. The higher the molecular weight, the larger, more polarizable electron cloud, the higher your boiling point is going to be. Now, if you look at the polar series, the one on top in red is a polar series. I mean, you would expect, well, if they're fairly comparable things, then it's all going to be about LIMPEC once again. The dispersion forces of a larger, more polarizable electron cloud increasing your boiling point. And you see that for those three. But water here is a big anomaly. Water didn't really seem to follow our trend. Even though it's polar just like the rest are, and it's really, really small, you would expect it to have, you know, boiling point somewhere way down here. And water shouldn't be a liquid at room temperature. It should be a gas at room temperature based upon its size. Well, that's because there's something going on special with water. So water is an anomaly here that kind of goes against our trend. So when we had similar things increasing in molar mass, it's not always just about the larger, more polarizable electron cloud. And that's because there's another special type of dipole-dipole, a super strong type of dipole-dipole that makes water held together much more strongly than the others. And this is hydrogen bonding. So the dipole-dipole interaction between hydrogen that's bonded to an NO or F in a molecule. So if we have a polar molecule and we have a hydrogen that's bonded to an NO or F, we end up with an unusually strong type of dipole-dipole. So strong and different and anomalous that it gets its own name. It's not a dipole-dipole interaction, it's hydrogen bonding. Now the way I teach my pre-AP chemistry students to remember this is it's dipole-dipole unless it's strong enough to be hydrogen bonding. HNOF is like enough. So if it's strong enough, polar molecules are hydrogen bonding. And this is a very, very, very strong type of attraction. Now in AP chemistry, you need to have a deeper level of understanding than just that. So you need to understand at its heart what is really happening with these types of things that we call hydrogen bonds. So hydrogen bonding is a very, very important type of bonding in everyday life because water is such a common substance. And many molecular substances display hydrogen bonding, and that makes them stick together significantly stronger than you might think. So hydrogen bonding plays a huge role in body chemistry. Now, hydrogen bonding arises in part from the high electronegativity of nitrogen, hydrogen, or nitrogen, oxygen, and fluorine. So the deeper level understanding you need to get with this than you may have talked about last year is one. If you look at where they're on the periodic table there in the upper right, these are our most electronegative substances that are commonly involved in bonding. So they have high electronegativities, which mean they are great at grabbing electrons. Now the second component to the special nature of hydrogen bonding is the hydrogen. Now when hydrogen is bonded to one of these, what it really does is it exposes the hydrogen nucleus. So you have your fluorine and you have your hydrogen, and they're sharing the electrons, but those electrons, because fluorine is so electronegative, are shifted very close to the fluorine. So that makes this a significantly negative situation. And this is significantly positive situation. But it does more than that with just hydrogen, because any large polarity difference or large electronegativity difference would do this. But what happens here is hydrogen is basically a proton and an electron. And when you move the electron away, what you're left with is an exposed nucleus. So why this is such a strong force is these things are highly electronegative, and when you pull that electron away from the hydrogen atom, you expose the hydrogen nucleus, and it's a very small distance. Remember, distance kills attractive forces? Well, when you have this exposed hydrogen nucleus next to other negative things, it's going to be a very strong type of interaction. So the key here is the big electronegativity difference and the exposing of the hydrogen nucleus. And that's why it's hydrogen bonding. This happens with hydrogen, and that's about it. Now, to summarize what we've been looking at, this is a nice flowchart that you should become familiar with because it really breaks down the different things we looked at. So our van der Waal forces, those are going to be these forces over here. Force 1, 2, and 3 that we talked about. Hydrogen bonding, dipole-dipole, and our London dispersion forces. And then over here we have our non-neutral attractions, and those would be a little bit stronger in general, although we already looked at how something like a London force can be very, very strong. So those are the bottom of our forces. Well, how do we know what we've got? We'll start at the top of here. So look at what you've got interacting. Do you have molecules or do you have ions? If you have ions, remember it's not going to be one of the van der Waal forces. It's going to be ion-dipole or tip ion to ion, which would be ionic bonding. If you do have neutral substances, so there are no ions involved, then what you're really looking at is the polar molecule situation. And remember, if it's nonpolar, it's going to be London forces, and that's it. If it's polar, it's either dipole-dipole or it's hydrogen bonding. So this is an important distinction. Is it strong enough to be hydrogen bonding? And remember, in addition, all of these forces have London forces. So all of our van der Waals forces, not just dispersion forces, but dipole, dipole, and hydrogen bonding, all of them can also have London dispersion forces, which in a very large molecule, because of L'impact, then become even more relevant than the dipole, dipole, or other interactions. And that ends our notes over the first part of chapter 11.